right, so let's look at a super simple type of, well, I shouldn't say simple, a super common type of dynamics problem, and that's the problem involving a ramp. So here we have a child that has a mass of 22 kilograms, and they slide down a slide that makes an angle of 22 degrees with the horizontal. Assume friction exerted by the slide is negligible. So let's first draw a free body diagram, then we'll calculate the magnitude of the normal force acting on the child, and then we want to find the magnitude of the acceleration of the child down the slide. The chili. Okay. So first I'm wanting to kind of sketch out this situation, right? So first, let's draw the slide. I'm going to draw the slide like a ramp. You'll see why in a minute. And then we have a child sliding down the slide. All right, so there's my child. All right, very simplified shapes here, but nonetheless, a couple things I know, right? We're told the angle here is 22 degrees with respect to the horizontal, so that's that angle there in the corner. All right. Let's see. So what I like to do is once I've kind of sketched out this diagram here, I like to draw my forces on it. So we've got, well, actually, effectively what we're drawing here is a free body diagram, which I'll draw separately just for posterity's sake. But we've got the force of gravity acting on the child. Force of gravity acts straight down towards the center of the earth. I'm going to draw it extra big for just reasons you'll see in a moment. Other force, well, we have the force of the slide on the child. We call that the normal force, since it is perpendicular. And there's our normal force. So if I'm drawing just a free body diagram, we've got, well, sketching it here quickly. Normal force up and to the left, force of gravity straight down. And hold on a second, I gotta let my dog in the room since she's sniffing under the door. I guess my dog wants to learn some physics too. Okay, so we drew a free body diagram. Step A is done. Let us now calculate the magnitude of the normal force exerted by the slide on the child. All right, so the trick to dealing with a problem with a ramp is to realize that we've got the child moving down the ramp. In fact, they're moving down the ramp with a faster and faster speed, meaning they're accelerating down the ramp. So it's going to be very convenient for us to tilt our coordinate system. So kind of basically every time you're dealing with a ramp problem, you're going to want to tilt your coordinate system. So I recommend calling the direction of acceleration, so down the slide, positive x. So we'll call down the ramp positive x. Positive x, and then perpendicular to the ramp, positive y. All right, so here we have our coordinate system. So our coordinate system always has to be orthogonal, meaning like perpendicular, which we do have here, down the ramp and perpendicular to the ramp. So that's good. Just be careful. Sometimes you might want to make a coordinate system where the angle between them is not 90 degrees. You can't do that. They always have to be orthogonal. All right, so looking at this normal force, what do we know about it and what can we say? So normal force is in the direction, in my y direction, so that's awesome. My x direction is down the ramp. Force of gravity is neither pointing directly in my y or my x. So actually I have to break up my force of gravity into its horizontal and vertical components. I shouldn't say it, my x and y components, excuse me. So let me actually, I'm going to change where I wrote force of gravity. Or write it on the other side. So we need to draw the components of gravity. One component acting in my y direction and one acting in my x direction. So for the force of gravity, we've got our y direction perpendicular to the ramp. So, but my gravity is kind of pointing down, so to speak. So this is going to be my x component, excuse me, or my y component of gravity. All right. So basically, that component I can draw it in the direction away from the ramp or towards the ramp. Since the force of gravity is pulling the child into the ramp rather than away from the ramp, it's in that direction. And then for my x direction, the x component of gravity, that's acting down the ramp. Right? So the reason for that is that the gravitational force is pulling the person or the child down the ramp, not pushing it up the ramp. All right. So if I were to draw a modified free body diagram, so what I mean by that is just drawing the drawing all the forces in their component form as necessary. So basically, all my forces are acting in the x and y direction, so it makes it really easy to sum. So my normal force is drawn as is, since it's in my y direction. Then we have my y component of gravity and my x component of gravity. And again, sorry for those vectors being kind of wobbly. It's this pen. Okay. So that's a modified free body diagram. So what's interesting to see here, and I kind of drew it in a leading way, is that my normal force here is the same magnitude as my y component of the gravitational force. Why is that? So that is because our normal force, so our child is accelerating down the ramp. It's not accelerating off the ramp at all. It's completely in my x direction. So my y direction, those vectors have to sum to be 0. They have to cancel out. So my normal force here is going to equal my y component of gravity. Right. So in order to figure out what that is, excuse me, we have to do a little bit of math, a little bit of geometry. All right. So because I've drawn a right triangle here for my ramp. Now we need to figure out where this angle theta is in this right triangle. All right. So where is the angle theta? So we can look at first this triangle just to reason it out. Wow. So we've got theta in this corner here. This angle in the corner, this angle is 90 degrees, which means this angle up here is 90 minus theta. You also see that this big angle there is 90 degrees, which makes this angle right here the angle theta. All right. Kind of long story short, if you always draw your diagram with your kind of, so to speak, your y component first for gravity, then your x component, that top angle is always going to be theta. It's not the bottom angle. Okay. So then my y component is adjacent to the hypotenuse, where the hypotenuse is the gravitational force. So we have the force of gravity times cosine of theta is our normal force. So we have the normal force is equal to force of gravity, well it has the expression mg, times the cosine of theta. So plugging in numbers, we have the mass of 22 kilograms, g being about 10 meters per second squared, and our angle of 22 degrees. That gives us, once we plug it in our calculator, 204 newtons as for our normal force. And then finally here, calculate the magnitude of the acceleration of the child down the slide. Right. So we can look here at our modified free body diagram and see that there is only one force here that is causing our acceleration, and it's the horizontal component of gravity. So basically we are summing our forces in our x direction. That's equal to mass times acceleration. The only force, so if we're summing our forces, is the x component of gravity, and that's equal to mass times acceleration. So here, for our x component of gravity, looking at that triangle we sketched out, that's opposite my angle, and my hypotenuse is the total value for gravity. So we have the force due to gravity times sine of theta is equal to mass times acceleration. Where we can rewrite the force of gravity as mass times acceleration due to gravity. What's convenient here is we have less numbers to plug in because mass cancels out. So the acceleration of this child is equal to g times sine theta, which again, plugging in 10 meters per second squared and 22 degrees, we end up with 3.75 meters per second squared. Now what's particularly interesting here is that this expression for acceleration is independent of mass. So it doesn't matter how massive this child is. It could be a full-grown human being sliding down the slide. As long as the slide's frictionless, their acceleration is going to be the same. Their acceleration is entirely dependent on the angle of the slide. And in fact, we also see as the angle increases up to, let's say, well, actually a value of 90 degrees, the sine of whatever that angle is will also increase, leading us to a larger acceleration, which is what we expect. A steeper slide is going to cause the child to accelerate at a faster rate. So it's important that we have a sine function here, where the limit of that is actually going to be the sine of 90 degrees. All right, so sine of 90 is a value of 1. I don't know why my brain had a little brain fart there, but sine of 90 degrees is 1. So at a 90-degree angle, our acceleration is just g, the acceleration due to gravity, which makes sense because when the slide is vertical, the child is in free fall. So, anyway, dealing with objects on ramps is very typical for a physics type problem. So the key to solving these problems, again, is tilting your coordinate system so that the direction of acceleration is entirely in one of your directions, x or y. So here it was convenient to tilt our coordinate system to be laying on the ramp. You could, in theory, solve this problem with calling horizontal your x and vertical your y. The reason why that would be annoying is because now both your normal force and your gravitational force are at angles in your coordinate system. So you have to deal with a bit more math, and then also your acceleration would also have to be broken up into components in which you have to combine into a total acceleration value. So it's doable and it's acceptable. It's just harder and more annoying to do. Whoa. Okay, well, with that, sounds like we're going to stop here. I hope that was helpful.